Now let's talk about quantum mechanics, the nuts and bolts of the theory of the small particles. The laws of quantum mechanics rest on fundamental postulates. In this section, we're going to be looking at some math. It's the math that's foundational to quantum mechanics, but we'll talk about these ideas and words too, while remembering that the mathematical physics behind quantum theory is really why physicists trust it so much. This math makes sense, it's developed from first principles, and it matches the way the world works. There are several fundamental postulates involved in this theory. One is that all information in a system is provided by what's called the wave function. The second is that the motion of a non-relativistic particle is governed by a single equation called the Schrödinger equation, developed by Edwin Schrödinger, one of the founding fathers of quantum theory. And the third postulate that the measurement of a system is associated with a linear mathematical operator called a Hermitian. So, the first postulate, all information about a microscopic system is provided by its wave function. Well, what is a wave function? Wave function is a mathematical description of the amplitude of the wave. Remember, any particle can be thought of as a wave at any position in space. We can manipulate the wave function, we can combine wave function of different particles, and we can evolve the wave function in time. And that's the core of quantum theory. The wave function can be positive, negative, or complex valued. That's involving the square root of a negative number. The squared amplitude of a wave function at a position is equal to the probability of observing the particle at that position. That's easy to understand, and that gives the fact that particles are not found at one location in time, because the wave function has extent in the x direction, and so its square does as well. The wave function can evolve and change with time, and the mere existence of a wave function implies the wave-particle duality that we've said is foundational to quantum theory. Now, all the postulates are weird at some level. The weirdness of postulate 1 is pretty obvious, because it means that particles are not localized. They don't have a well-defined position. In classical physics on the left, you say the particle is here. I measure it, its position is x. In classical theory turned into quantum theory, we have a quantum particle described by a wave function. And all we can say is that with some high probability, or some probability that we can specify, the particle is somewhere in this region. And that's really the best we can do. Postulate 1 is weird for another reason, because of the uncertainty principle. At any given instant, the position and momentum cannot be both known with certainty. So in the classical world, on the left, a particle can tell you its properties. Hi, my name is so-and-so. My position is here. My momentum is this number. My energy is this number. But a quantum particle on the right cannot be so sure. It, for example, will say, well, I can tell you my exact position, but then I can't tell you my momentum. Or I could tell you my exact momentum, but then I couldn't tell you my position. I could give you a pretty good estimate of my position, but then I'd have to give you a bad estimate of my momentum, and so on. You get the idea. It sounds very unsatisfactory, and it is a fundamental attribute of quantum theory. It's also weird because a subatomic particle can be in multiple states at once. On the left, a classical elephant only has two hypothetical valid states. It can be gray or multicolored. Imagine there are just two types of elephant. But in the quantum world, the elephant can be gray or multicolored, or be some superposition of gray and multicolored at the same time. That's definitely weird. The second postulate is that the motion of relativistic particles, or non-relativistic particles, is governed by what's called the Schrödinger equation. And here you see it in mathematical form. To me, I'm sorry, as a physicist, this is beautiful. I realize it's slightly intimidating. But solving the Schrödinger equation is something that physics students do all the time. It's not that hard, and it tells you about particle properties and how they evolve. The Schrödinger equation is a wave equation whose solutions display interference effects. That's interesting because it means that particles can interfere with each other. We tend to think of particles just colliding with each other or not colliding, end of story. But since particles can be waves too, they must have wave-like properties, including interference. The Schrödinger equation is also important because it's a unitary equation, and therefore it's reversible in time. That's fundamental because that means any property we see of microscopic particles and their behavior that flows forward in time could, in theory and in principle, flow equally well backward in time. The time arrow for a microscopic system is reversible. Now in practice, this equation is only easy to solve for a couple of particles. Any more than 3 and it becomes hard even for a computer to solve. How weird is this postulate? Well, this is very weird. This postulate tells us that a quantum mechanical particle can tunnel through barriers rather than going over them. On the left, a classical ball simply doesn't have enough energy, if it's not pushed very hard, to climb up the hill. But in the quantum world, the ball, given the same amount of push, could, with some small probability, tunnel through the hill and get to the other side, despite having formally insufficient energy. That's definitely weird. It also says that quantum particles can take all paths. Imagine a classical mouse presented with a maze. The classical mouse can only take one path, specified by Newton's laws and his laws of motion, to get to the cheese. A quantum mouse, however, has, through Schrödinger equation, a non-zero property for the particle to take any of a number of possible paths. All are equally valid and all coexist. This was formally worked out in what's called Feynman's path integral. That was a formulation of quantum mechanics done in the 1950s that really led Feynman to get his Nobel Prize. The third postulate is that the measurement of a quantum mechanical system is associated with a mathematical operator called a Hermitian. Without worrying about the math, the interesting facts about this postulate are that certain properties can only achieve a certain discrete set of measured values, not an infinite number of measured values. This operator implies that measurement is inherently probabilistic, and that measurement necessarily alters the observed system. These are unavoidable features of the theory and the equations. There's weirdness here, too. It means even if the exact wave function is known, the outcome of any measurement is probabilistic. On the left, the classical elephant is in the state we see before the measurement, and after the measurement, it's in an equally known state. It's a deterministic outcome. For the quantum elephant on the right, which could have a superposition of properties between multicolored and gray, we don't quite know what the outcome is, because the outcome's probabilistic too. And that's the best we can do with any experiment. Measurement alters the observed system. This is also related to the Heisenberg uncertainty principle. So the classical elephant is sitting here looking like this before the measurement, and after we measure it, it hasn't changed, it hasn't moved, the state of the system is unchanged. But the quantum elephant on the right, in a superposed state of multicolor and gray, has actually been changed by the measurement. It's actually been changed into a fully composite system. Another weirdness of this third postulate is that properties are actions to be performed and not labels to be read. So a classical elephant is here. It has a color that we can recognize as gray, and it has a size that we can easily say is large. The position of the object is independent of its measurement, and it's just read by the observer. But the quantum elephant is not so sure. Its position is an action performed on an object which produces a particular result. In other words, even simple physical properties like position or momentum do not exist independent of measurement, unless you're called a non-realist. So now we're getting towards a philosophical part of quantum theory that's extremely strange, because we tend to think that things exist independent of our measurement of them, and it's just a matter of us getting the measurement. Quantum theory says it's not so simple. And that's the end of this topic.